nonlinear systems get quite a bit more difficult to solve. So we're going to talk about linear systems, and then what we're kind of our goal is to translate systems of equations into matrices, and then use matrix techniques to work on systems of equations. Because with the matrices you can do some manipulations with matrices that make the problem much easier than doing row operations. All right, so our idea for three-variable systems, usually it's difficult to use substitution for three-variable systems. It's possible, but it's kind of complicated. So what we're going to do is use elimination. But since we have three variables instead of two, we're going to repeat the steps. So I'm going to say use elimination repeatedly. Now when we have a three-variable system, our goal is to make the system we're going to do some operations, we're going to do elimination, look like something like this. So this is just an example of how we want to end with when we solve a three-variable system. X minus y plus 2z equals 1. In the second row, we just want a y and a z. And then in the third row, we want just a z. So we're going to use elimination to get rid of the x that was here and the x that was here, and we're going to use elimination to get rid of the y that was there. And then what this lets us do is we can see that z equals 2. We can substitute that into the next equation, and we figure out that y equals, so I'm going to put this from here, we can figure out that y equals 1 if we substitute z equals 2 there. And then we can substitute both of those into that first equation, the y and the z, and we figure out that x equals -2. So we call that back substitution. When we get our system of equations in this form, where there's no x here and there's no x or y in the third row, we call that row echelon form. So the problem may ask you to solve the system of equations by getting it into row echelon form. So when it looks like this, we call it row echelon form. And just one little detail, technically row echelon form, there's no coefficient on the z. We can still get the solution if there's a coefficient on the z, but row echelon form, we have just a 1 in front of the z. The process that we use to get our system into row echelon form is called Gaussian elimination. Gauss was a very famous mathematician. I don't think he invented it. I think he was one of the first to kind of formalize the process. And the steps that we use are called row operations. Just so we know our vocabulary when you see the problems, the problem might ask you to use Gaussian elimination to solve the system. Or it might say, use row operations to get the system into row echelon form. Our row operations, we already know what they are. I'm just going to list them out so we So we have them in our head, what we're actually, the row operations that we're actually talking about. One of the row operations is we can exchange two rows. So we might have one row that's already missing an X. We can put it in the second row if we want. So we can switch the order. We can multiply any row by a number. So over here we multiplied both the top equation by -3. That's one of the row operations we're allowed to do. And we're going to say the number, we don't want the number to be 0. Because if we multiply by 0, then we just get all zeros. And that's not going to be helpful. And then the third row operation, we did that with our two variable system. We're going to add, and I'm going to put in parentheses, or subtract, a multiple of one equation to, and I'm going to say or from, if we're going to subtract, just to be grammatically correct, a multiple of another equation. And replace the second. And it's the replacing part that lets us get rid of this x and get rid of this x and y. We replace the equation after we do that. So we're multiplying a row by something, multiplying another row by something, and then adding them together. And then we replace the row by what we get after we do that. So those are our row operations. That's the process we use for two variable systems. We just didn't give it a special name when we did two variable systems. It's still row operations. And this just helps us keep track of what we're doing with three variable systems because there's more stuff going on. All right, questions here. All right, so what I want to do, I just want to go through a couple of examples of doing some row operations. We'll talk a little bit about the geometry of what's going on, and then we'll set up an example of one kind of classic problem in three variable systems. All right, so let's take a look at an example. Let's say our system is x minus 3y plus 2z equals 1, 2x minus 5y plus z equals -5, and 3x plus y minus 2z equals -1. Let me make sure that's what I want my system to be. Yes? All right. There's my system. What I usually do to help me keep things straight is I call this row 1 or equation 1, 2, and 3. So our goal, the idea here is we're going to use the first two equations to get rid of this 2x. We're going to use the first and the third equation to get rid of this 3x. So after our first two steps, we're going to get rid of the x's. Then we'll be able to use these two equations to get rid of the y's, to get rid of this y. And then we'll have our system in row echelon form. So you don't have to do it this way. It helps me keep track of what we're doing, and also helps me describe what I'm doing. Also helps me figure out where I made an arithmetic error if I go back and look at what I'm doing. because I usually make arithmetic errors. So for the first two equations, what are we going to do here to get rid of this 2x using these two equations? If we're doing elimination, multiply this one by -2. So I'm going to say multiply 1 by -2, and we're going to add to 2. So my first row doesn't change, so I'm going to write what we get after we do that step. X minus 3y plus 2z equals 1. And I'm not going to write out the multiplication. I'm going to do the arithmetic in my head. So we get -2x plus 2x. I get a 0x. I get a 6y minus 5y. So I get a y here. I get a -4z plus z. So -3z. And I get a -2 minus 5. I get a -7. So that's what I get after I did this step. Now I'm going to use the first equation and the third equation to get rid of this 3x. So what do I want to do with the first and the third to get rid of that 3x? Do we want to multiply 1 by -3? And add to 3. So from here, we're doing just like we did here, or just now we're doing it with these two. So now I'm going to write the result that I get there. So I get -3x plus 3x, get a 0x there, get a that's good, 9y minus y. Did I do that right? No. Positive 9y plus y. 10y. I get a -6z plus a -2z, so minus 8z. And I get a -3 plus a -1, so a -4. So this is my system after I've done these two steps on the first system. And then we get 1, 2, and 3. And now I'm going to use these two equations to get rid of this 10y. So I'm going to write what we get after that. So the first row doesn't change. The second row is good the way it is. All right, so with these two equations, what do we want to do to get rid of that 10y? I'll get us started. We want to multiply. Multiply 2 by -10 and add to 3. That's going to get rid of that 10y. So -10y plus 10y, I get a 0y. -10 times -3, I get a 30z minus 8z, so I get a 22z. And here I get a 70 plus -4 equals 66. Now we could come up with our solution from here, but I want to get my system in row echelon form just to do the final step. So what are we going to do to this third equation? To get rid of that 22. Divide by 22. All right, so then finally, my final system in row echelon form is going to be this. Z equals 3. And then I plug Z into the second equation, and that tells me that Y equals 2. I plug Z equals 3 and Y equals 2 into the first equation, and I get that X equals 1. And my solution is the ordered triple 1, 2, 3. So instead of an ordered pair, we get an ordered triple. And we talked last time with a 2-variable system, we're looking at for where lines intersect. With a 3-variable system, we're looking for where planes intersect. These equations describe 3 planes. So this is telling us that these 3 planes would intersect in the point 1, 2, 3. So we can see when I said use elimination repeatedly, there's a bit of repetition. Linear algebra, we're kind of doing, this is a piece of linear algebra. Linear algebra is a little on the tedious side, but it is essential. You solve systems of equations in math all the time. So it's an important skill. But eventually, we're going to be thankful that computers are really good at doing this stuff. That's one thing that computers are really good at. All right, let's look at one more example. Questions on what we did there? So these were what I wrote in blue, those are my row operations. The entire process was Gaussian elimination. And here's my system in row echelon form. And you can imagine how much the layer of difficulty that it would add if you had a 4-variable system. It gets more and more complicated. Yeah?
When you're doing your row operations, you have to eliminate x, then y, then z.
Yes.
And you start with z and y. Like it's easier to eliminate z first. Can you do that?
You can, but you want if you did that, I would write them in a different order. So I would write z, y, x, something like that. But you can do that. So I would also always write write them in the order of the variable that you're going to eliminate first. And usually, sometimes that makes it easier, but usually it's not much more difficult just to leave it in the original order and do the row operations the way they are. Okay, so let's look at another example. This one's not. We'll see something interesting that happens here. So we're solving this 3-variable system. So this third equation doesn't have a y, so I just left a space there. And when we start talking about matrices, we'll do something specific when that happens as well. So that's our system. We want to use row operations, do Gaussian elimination. So our first step is going to be use these 2 equations, equation 1 and equation 2, to eliminate this 2x. So what are we going to want to do? Multiply 1 by -2, add to 2. So my first row doesn't change. X plus y plus z equals 2. When I do this operation, I get a 0x, I get a -2y plus 3y. So we get a y, and I get a minus 2z plus 4z, so plus 2z, and I get a minus 4 plus 5, so that equals 1. And now we're going to use the first row, or the first equation and the third equation, to eliminate this x. So what do we want to do there? We can multiply by -1 and add, or we can just subtract. Either one is fine. I'm just going to write subtract 3 from 1. It can be, if you're prone to making sign errors, plus minus errors, it might be easier to multiply by -1 and add, but we get the same result. So x minus x, we get a 0x. Y minus 0. Y, we just get a 1, right? Y minus 0, we get a 1y. So sometimes when you do row operations, even if there's nothing there, after your operation, you might get a variable there. Z minus Z minus negative Z plus 2Z, 2 minus 1 equals 1. Do we see what's going to happen here? Not yet? Okay. We're going to use now 2 and 3 to eliminate this y. So what are we going to do there? You could multiply by -1 and add, or I'm just going to say subtract 3 from 2. So I get my system x plus y plus z equals 2. Y plus 2z equals 1. Y minus y, 0. 2z minus 2z plus 0. 1 minus 1. 0 equals 0. What does that tell us? Yeah, we get an infinite number of solutions. And again, your book will put the answer for an infinite number of solutions in a kind of a strange form. If you get 0 equals 0, 1 equals 1, 5 equals 5, if you get an identity, that tells you get an infinite number of solutions. And if you get 1 equals 0, that tells you get no solutions. So really, anytime you see two equations that are duplicates of each other, that tells you you get an infinite number of solutions. All right, but let's talk about the geometry here for a second. Because three planes can intersect in a lot of different ways. So let's look at a picture. Here are three parallel planes. That would be no solution. That would be a 1 equals 0 or something like that. You can have three planes intersect in one line. There's that possibility. You could have two parallel planes that are intersected by another plane. That would be two lines where they intersect. The most likely scenario is somehow your planes are going to intersect in three lines. And here's the possibility where the three planes intersect in one point. So the problems where we find a nice solution like 1, 2, 3, those are pretty contrived because in general it's relatively unusual that three planes would intersect in a point. One of these three possibilities is much more likely for any three particular planes. So that's our geometry, what we're looking at here. All right, questions? Okay, the last thing I want to do is set up a specific type of problem that's a very, very typical three-variable system problem. We want to find the equation of the parabola. Y equals ax squared plus bx plus c. So if we graph that parabola, if we graph this, we get a parabola that goes through three specific points. 1, 6, negative 1, 4, and 2, 13. So what are we going to do here? We might be thinking, well, what does a parabola have to do with the systems of equations? Well, what does each one of these give us? What is this? In this ordered pair. Isn't that an x? And that's a y? Isn't that an x and that's a y? That's an x and that's a y? We're going to plug those in. It's not a coincidence that there are three of those. So from 1, 6, we plug that in and we get 6 equals, x equals 1, a plus b plus c. From negative 1, 4, we get 4 equals, negative 1 squared is 1, so a, x is negative 1 here, minus b plus c. And from 2, 13, we get 13 equals, 2 squared is 4, x is 2, so plus 2b plus c. And if we write this the way that we have been writing these, we get a plus b plus c equals 6, a minus b plus c equals 4, and 4a plus 2b plus c equals 13. And there's our system of equations. Instead of x, y, and z, we have a, b, and c. And from there, we can use row operations. Row operations here. So we do solve the system exactly like we've been doing. Eliminate a, eliminate these a's, eliminate these b's. And once you do that, you would see that a equals 2, b equals 1, and c equals 3. So my answer, my parabola, would be y equals 2x squared plus x plus 3. And in general, we can always find an equation for a parabola if we have 3 points that it goes through. So we need 2 points to make a line. We can write an equation of a line with 2 points. We need 3 points to find an equation of a parabola, which is kind of interesting itself. All right, questions? Okay. Look at that. It fits on one line.